In this video, we want to learn about void discharge. Whenever there is a void inside an insulation system, we want to see what is the pattern of such discharge. So basically, we have here a ceramic material, and you can look here, there is a hollow, there is a void inside this ceramic insulator. So I will put it between two parallel electrodes like this one. Okay, and this parallel electrode will ensure that we will have a uniform electric field. So if there is any discharge, it will be coming from the void which is inside the insulation system. So now what I will do, I will go and apply high voltage, and we look to the PT pattern and see how the PD from a void looks like. Now I will start applying the voltage. I will start to increase the voltage. Here is the voltage level, and this is the pattern of the PD. Okay. Nothing still. Now you can see here. You can see here the discharges at both the positive peak and at the negative peak as well. Symmetrical discharges. If we increase more, so you can see here very clear discharges, and these discharges are coming only from the void. Now, why the discharge happened in the void? Please join me in the small presentation discussing the physics of the void discharge and why we have this type of partial discharge internal the insulation system.
Hi everyone, and welcome to this short presentation that will talk about the internal discharge. And we'll say internal discharge, this is different than external discharge. We describe the external discharge due to dry surface discharge or due to wet surface discharge. But this discharge is inside, internal of the insulating material, not external. So something that you cannot see, like in the other type of discharges. And in this short presentation, I'd like to answer a couple of questions. The first one is why we have or how they look like those internal voids that will initiate the internal discharge inside the electric material. So they could be coming in different shapes, like in A here, it is a sort of a horizontal void, or as a spherical void, or a vertical void. These defects are inside the bulk of the material. And again, this bulk material could be cable, XLPE, could be polymer, could be any type of outdoor insulator, could be any type of dielectric material, could be a void inside the oil in the transformer tank. Also, the void can be as a result of the interface between two different dielectric materials. And because our more focus is in outdoor insulators, let's see how these defects can be initiated or can be found inside outdoor insulators. And basically, here we talk about two different common problems or internal voids inside outdoor insulators. We'll talk about first ceramic insulators. Now, ceramic insulators, cap and pin, we have basically cement. This cement will hold the ceramic structure with the metallic cap and pin. Now, due to aging, voids start to develop inside this cement structure, or cracks, sometimes a crack inside those structure. So that will lead to field enhancement, as we'll discuss in the coming slide, which will lead to internal discharge. So in ceramic insulator, basically the main cause of internal voids is aging. When it comes to outdoor insulators, which is the polymeric one, or basically the silicone rubber, which is the main type of outdoor insulators, the void comes or happens at the interface between the housing and the core. So basically, during the manufacturing process, you have the core, and you have the inject the mold of the silicon rubber material. So sometimes there will be some voids between the housing and the core. So this is an interface type of void. The question is why we have field enhancement, why we have discharge inside these voids. Again, let's use this example for demonstration. So basically, this is a dielectric material, and we have inside a void here. And I'm calculating the electric field along this line, let's say from point A to point B. So when you see here, this is the electric field along the distance. So when it reaches the void surface or starting of the void, you will have an increase in the electric field. Now, the value is not important, but it goes from 2 to around 4. So it's almost double. The electric field inside the void doubled. Why is that? Again, because of the basic formula that we used before, epsilon R1 E1 equal to epsilon R2 E2. Now, this is valid when you have interface of two different dielectric material. So if this is ceramic or silicon rubber, epsilon R1 will equal to or will be from 3 to 5. And for air, epsilon R2 will be around 1. So the dielectric constant of the polymeric material is larger than the dielectric constant of air, which will result that field enhancement inside the void, E2, will be higher the electric field in the bulk of the material. Add to that, the breakdown of air is much less than the breakdown of the bulk of the dielectric material. So if the electric field E2 reaches a level of breakdown, which is 22 kilovolt per centimeter RMS, or 30 kilovolt per centimeter peak, then you will start to have discharges. So let's now try to have a look or a closer look why we have this pattern of discharge that we have shown in the clip. So here we have a sample model of dielectric material that has a void. We have here one void and there is another void. And we apply a sinusoidal. Now, when you apply the sinusoidal, and so number 2 is the voltage, number 1 is the current pulses, which is basically the partial discharge. So when we increase the voltage here, we can see here there is no discharge because the electric field inside the void is still not high enough to start any or to initiate any partial discharge until it reaches around this level. Then you start to see sort of discharges happened inside the void. You go up here until you reach certain level, which is the partial discharge will start to disappear. And then when you go to the negative cycle, the same thing. So you will see that there are discharges during the positive cycle and during the negative cycle. And that's what we have seen inside the void. Now there are some challenges, especially if you want to apply online monitoring of those internal discharges. We'll try to in the future to show you some techniques that can be used to capture these specific type, which is the internal discharges, and we'll try to compare different methods. Until then, thank you for joining me and have a good day.